You wouldn't know it to look at the sky, but something is seriously wrong with the universe. Astronomers have suspected it for some time. Now they're pretty sure. For one thing, the universe may be billions of years too young. For another, part of the universe has been missing, a big part. Fact is, there have been several discoveries recently that threaten to topple our understanding of the universe like a house of cards.
Scientists generally agree that the universe is very, very old. But now there's a theory that it may actually be younger than it looks if you look closely enough.
What in the world is going on with the universe? Astronomers have found, calculated, or conjured up outlandish, appalling things. Whispers from space left over from the moment of creation. Dark stars, dwarf stars, stars that eat each other. Stars clumped in galaxies, and galaxies clumped in larger, stranger structures. Only recently have we even begun to understand the scale of it all. We have discovered things so small.
At a 10 millionth of a trillionth of a trillionth of a trillionth of a second is the earliest time we can really talk about.
And expanses so vast.
That's expanded by a fraction of a million times a trillion times a trillion.
The researchers need a special notation.
A billion times a trillion degrees.
To write out the incredible distances and magnitudes involved in understanding the universe. Suppose we were to begin with Peoria.
Peoria is the center of the universe.
Well, not exactly, but the director of the planetarium has built a scale model of the solar system in and around his Illinois city.
How's it going, Dave?
Morning, Phil.
Morning. A little bit to the left. I think you missed a spot.
A sunspot,
There.
get it?
You got it.
The sun in this model is 36 feet high. Mercury is closest to the sun, of course, just around the corner at the school supply store. On that scale, the Earth is 6 blocks away at the Amoco station. Earth is open 24 hours a day. And Mars is 7 blocks beyond Earth at the TV station. Mars has life, or at least television reporters. Pluto is smaller than a golf ball. It's a full 40 miles out of town. And if you think rural Illinois is empty, try the universe. The 40 miles to Pluto, on Peoria's scale, represent 3.5 billion miles. On the same scale, the nearest star, Proxima Centauri, would be as far from Peoria as the moon. This isn't helping, is it? Okay, forget Peoria. Our sun is bright because it's close, just 93 million miles away. Stars are suns, but farther away. The nearest star is 25 trillion miles away, so far that light from Proxima Centauri, light, the fastest thing in the universe, takes 4 years and 4 months to get here. They say the star is 4 1/3 light years away. Our sun is just one of the billions of stars in the galaxy we call the Milky Way. How far across is the Milky Way? Real far, 100,000 light years. And the Milky Way is just one of some 50 billion galaxies. It's a million light years to the nearest galaxies and tens of hundreds of millions of light years just to cross our galactic neighborhood. It has been said that someone looking at the universe is like an ant contemplating a skyscraper times a billion. So what human beings have done is bring the lights in the sky down to Earth. They've personalized the stars and named them like they name dogs and horses. This grouping of stars in the southern sky is known as Orion. The shepherds in ancient Crete decided it looked like a hunter armed with a club and carrying a shield made of lion skin. Cretan shepherds had great imaginations. How do we know what we know today about the universe? Well, we've been trying to understand it for a long time. The awful majesty unveiled by night has, down the ages, stirred us to wonder and worship. Prehistoric astronomers used elaborate monuments to mark the sunrise and the sunset. By 300 BC, Aristotle taught there were transparent globes around the Earth, on which were mounted the sun, moon, planets, and farthest out, a sphere studded with little stars. As late as the 16th century, most still believed the Earth was the center of the universe. There were a few people, like Copernicus, who thought the Earth circled the sun, but not many. Then, in 1608, an Italian named Galileo heard that you could make a spyglass with two lenses in a tube. He built one and aimed it up.
It was not until Galileo perfected the telescope around 1610 and pointed it at the Milky Way that he was able to say that the Milky Way was just millions of stars. And if you take a pair of binoculars on a clear night and look at the Milky Way, you'll just see that it's nothing but stars and clusters of stars.
Galileo's telescope magnified things about as much as a pair of binoculars, but that was enough. He saw that Venus had phases like the moon, that the sun had spots on it, and that the moon had mountains, and that Jupiter had 4 moons. Aristotle's perfect crystalline spheres were shattered, and the universe stopped being simple. And there were other strange things out there. Remember Orion? Well, down in the middle of his sword was a star that wouldn't focus to a bright point, no matter how powerful the telescope. The object came to be called a nebula, and over time, astronomers found many such fuzzy blotches in the sky. Fast forward a couple of centuries. By 1924, the big astronomical telescopes had mirrors as well as lenses to concentrate the light. The one on Mount Wilson in Southern California had a collecting mirror 8 feet across. Images were captured on photographic plates in slow, careful time exposures. In the dark chill of the observatory dome, Edwin Hubble was studying a distinctive kind of star called a cepheid variable. Astronomers use it as a distance marker because they know how bright nearby cepheids are. They know that the dimmer the cepheid, the farther away it is. Hubble was looking for cepheids in his photographs when he realized he was seeing an entirely separate galaxy, Andromeda, 2 million light-years away. A lot of those fuzzy nebulas turned out to be galaxies like our own. And the light from those galaxies looked redder than anyone expected it to be.
It's just like the pitch of a car engine, you know, as a car goes zooming by, you hear the engine kind of go, With light, when something's coming toward you, the spectrum gets shifted toward the blue. When it's going away, it gets shifted toward the red.
It was Hubble who recognized the significance of the red shift in the light. All those galaxies must be moving away from one another at terrific speeds. The entire universe was growing. The idea of an expanding universe surprised just about everyone and made a lot of scientists uneasy, even Einstein. Researchers wanted to believe in a universe that always was and always will be, eternal. But galaxies flying away from each other meant that once, long ago, they were clumped together. It meant something started them moving. The universe had a beginning. Today, it's called the Big Bang Theory. First, the universe was a bright, hot point, smaller than an atom. And the mother of all explosions, it started expanding. Eventually, the hydrogen gas in space cooled down and began to form stars and galaxies of stars. Galaxies flying outward, surfing along on the expansion of space itself. So now we can calculate the age of the universe. It's the kind of mathematics you do on a motor trip. If your speed is 30 miles an hour and you've traveled 60 miles, you can figure you've been traveling for 2 hours. The red shift tells us the speed of stars, and the milestone cepheid stars tell us how far they've traveled. When astronomers divide it out, it says the Big Bang happened 15 to 20 billion years ago. Long ago and far away. So who cares?
Well, we're answering one of the most fundamental questions that human beings can pose, and that is, how old is the universe that we live in? How did it begin? And what's its evolution? Those are major questions. Those are major philosophical questions, questions that religions have touched on, philosophy has touched on, physics is touching on, mathematics is touching on. And the people who are eventually going to come up with what is going to be accepted to be the right answer will make history of a kind. They will have contributed significantly to human knowledge. That, I think, is why it's such an important set of questions.
And there's been a growing sense, as the millennium approaches its end, that the right answer is on the tip of our tongues, so to speak. But not yet, not quite. Today's stargazers usually head for the hills. Hawaii's Mauna Kea, the Chilean Andes, Arizona's Mount Hopkins. Robert Kirshner works 8,500 feet up, hunting dying stars.
I really like coming to the mountain. I like getting away from all the 100 distractions that you have when you're busy, and people are coming in to see you about all kinds of things, and the makeup exam and all that kind of stuff. And to just concentrate for a couple of days only on the scientific investigation, only on what you're trying to do, it's very, very good.
Light pollution has chased astronomers out of the cities to lonely vigils in remote locations. Kirshner watches for the sudden flare-up that means a star has exploded, a supernova, or its smaller cousin, a nova.
The kinds of things I'm working on, these supernovae, which are events that come and go, if you don't get it this year or this month, that one is gone. You just lose the chance.
A supernova suddenly outshines its entire galaxy for a few weeks. If Kirshner and his colleagues can calibrate these cosmic flashbulbs, supernovas may prove even better mileposts than cepheids.
The game now for the supernovae, I think, is to find distant ones and to see if they really are the same as the nearby ones. Then we'll have a reliable tool to map out large-scale structure in the universe, and the supernovae, the Type 1 supernovae, look to me like a really good candidate for that.
It's easy to find where supernovas have been. There are clouds of dust and gas in space marking places where stars have blown up. But supernovas are rare. A galaxy of 100 million stars might have one exploding star every 100 years. So Kirshner watches and waits.
Well, the heroic age of observing has really passed. It used to be that you would be outside the whole night long, instead of sitting in a control room where a television brings the signal in and you're operating on a computer keyboard.
24,
okay,
get the CCD in the right mode.
It's hard staying up all night.
Is good.
But there's a kind of sense of adventure to it that is a little bit like being a kid and lying out in the snow and kind of figuring out the constellations. Some of that is good for you, too.
And we have liftoff. Liftoff of the Space Shuttle Endeavour.
In 1990, NASA launched a space telescope and named it for Edwin Hubble. Unfortunately, its mirror was made wrong and its first pictures were blurred. Astronauts had to go up and fix it.
Houston, let's go fix this thing.
We copy.
Move it out of the sun a little bit.
We had a good aliveness test.
Outstanding. Houston, Endeavour has a firm handshake with Mr. Hubble's telescope.
We copy that, Cubby, and there are miles galore down here.
It could be real exciting for the astronomical community, I guess, and for the whole world to see what Hubble really can do with a good set of eyeballs.
The out-of-focus pictures gave way to spectacular shots of interstellar dust clouds and the great galaxies of stars. In just one bit of the sky, a tiny patch that could be blocked by a grain of sand held at arm's length, astronomers found 2,000 galaxies. They were seeing better than they ever could before.
So one way of looking at it is if there was a firefly in Tokyo, and here we are in Washington looking at it, we could tell if there was another firefly 10 feet away, we'd actually be able to distinguish them.
In 1994, at the Space Telescope Science Institute in Baltimore, astronomer Wendy Friedman was using the newfound clarity of the Hubble to observe the heavens and stumbled into the cosmological controversy of the decade.
Yeah, I just wanted to ask you not to break out any observations until I give you a clear.
So when were these images taken?
She and her team, like Edwin Hubble before them, were looking at those milestone stars.
And the cosmic rays aren't nearly as apparent. For our work, we need a telescope out in space because what we're after is a certain kind of star. It's called a cepheid. And we have to be able to detect that kind of star against the background of a galaxy. And the Earth's atmosphere smears and blurs our view, and we can't detect those stars.
Friedman got the best readings yet on cepheids in a neighboring galaxy, and a measurement of its distance. Using the redshift speedometer, she calculated a new age for the universe.
Our preliminary measurements indicate that the age of the universe is somewhere in the range from 8 to 12 billion years. And that immediately brings about a conflict with other ages that have been measured.
That's a problem. Her universe is younger than some stars, and the age dating of stars is very accurate. Scientists can read a star's chemical changes like a clock.
When we look at a cluster of stars, hundreds or thousands, it doesn't really matter. What we have to do is go in and measure the brightness of the brightest star that's left in the cluster, that's still burning hydrogen in its core. And that star is the minute hand on the clock, because that's the star that is closest to burning out its hydrogen, closest to ending its life, and that's a direct measure of the age of the cluster.
But unfortunately, the star clock has been running 6 billion years longer than Friedman's universe.
We're very close to having a kind of contradiction between the ages of the stars and the age of the universe. This would be quite embarrassing, because you really shouldn't be older than your mother.
Clearly, if the universe is 10 or 12 billion years old, then there can't be stars in the universe that are 15 or 17 billion years old. That's not logical, at least if the entire Big Bang theory is right or even close to being right.
Wendy Friedman is well aware of the dilemma. She knows that, like many other puzzles about the universe, this one will probably be around for a while.
I think anytime you get a new tool, you get data that are of better quality than were possible to obtain in the past.
Yeah.
You learn new things, and yes, sometimes leads to confusion because there aren't answers for all of the questions that are being raised. But it's a healthy aspect of science and how science proceeds.
There's more to the universe than meets the eye. We can see only a small part of what's going on out there. What we call visible light, the rainbow from red to violet, is a small slice of a larger spectrum. But there are other ways of seeing. With the right technology, you can look at the world in everything from X-rays to infrared to radio waves. In the last few decades, the new tools have brought a previously hidden universe into view. Take the sun. Nothing to do but roll around heaven all day, right? But by using the X-ray part of the spectrum, astronomers can see the sun is a very busy place. Pictures made by X-ray detectors show there's a cauldron of nuclear reactions boiling beneath its surface. Using film sensitive to ultraviolet, we can see great plumes of superheated gases rising from the sun's surface. Our well-behaved, friendly neighborhood star is a continuing, self-contained thermonuclear explosion.
It's in high-energy astronomy where you really see that the universe is a violent place. It's not just made up of these good citizen stars that sit quietly fusing their hydrogen into helium.
The star-forming regions of the universe are often hidden from view by dust clouds, until infrared astronomy allowed us a way in. Now we can see clouds of frigid hydrogen gas condensing and starting to heat up as stars. The sky in the infrared is a strange and wonderful place. Once we learned where to look, we could peek into these stellar nurseries and snap some baby pictures. This is Hubble's view of the Eagle Nebula. The bright spots on the edge of these monstrous pillars of gas are brand new suns. But as spectacular as the pictures are, scientists owe much of their understanding of the universe to radiostatic, a whisper from the sky.
If you're listening to the universe with a radio telescope, it would mainly be a hissing sound. It sounds like steam escaping from a radiator.
They heard it first by accident. In 1965, researchers at Bell Telephone Laboratories had built a powerful listening station to hear signals from the first of America's communication satellites. But they were distracted by an ultra-low frequency hiss from everywhere in the sky. What they were picking up was energy from the bright flash that started the universe, an echo of the Big Bang itself.
Radio astronomy was the second big window we opened on the universe. The first big window was Galileo going and putting a telescope to his eyes and seeing what he could see with his own eyes, and then with film eventually. The next big step was radio astronomy. It's a great step forward in terms of discovering new things and understanding new things.
The discovery of the cosmic background radiation was a fatal blow to those who wanted to believe in an eternal universe. The Big Bang proponents had won. But the cosmic background radiation seemed to be smooth and even, coming from everywhere in the sky. Just what you'd expect from a universe that began from a single point. But then, why weren't the stars spread evenly through space? Galaxies should be moving steadily outward as the universe expands. Each should be moving away from all others like raisins in a rising loaf of bread.
Astronomers had thought that the universe was sort of expanding uniformly and the galaxies were just going along, and that the only motion we should see is the Earth going around the sun and the sun going around the galaxy. But in fact, what we saw was that the largest motion of all was the galaxy itself moving. And that really surprised astronomers, and the only conclusion we could come to was that something was causing the galaxy to move away from just the simple expansion of the universe. And after thinking about it for a while, our conclusion was that there must be a large group of galaxies near us.
When astronomers plot the position of galaxies in their computers, they find filaments and clusters and walls of galaxies. How could that be if radio telescopes were saying the energy of the Big Bang was evenly spread across the sky?
There had to be some seeds at the beginning. There had to be some small lumps in the early universe that are going to grow to create the structure.
So Smoot went looking for irregularities in the background radiation to show that the Big Bang explosion was uneven. In 1989, his instrument package went up on a satellite, the Cosmic Background Explorer. It found subtle variations in the energy left over from the moment of creation. Announced in 1992, it was one of the momentous discoveries of the century. The universe made sense again. Smoot later told the press these wrinkles in the cosmic background radiation were the largest structures ever seen and the oldest. He told reporters that it was like seeing God.
And that's the one that the press grabbed on because that's the one people could relate to. And that got spread all over and got much more attention, including people from philosophy and religion coming in and asking questions.
But if researchers could finally explain why there are stars and galaxies and collections of galaxies, that didn't solve their other major problem.
The problem is that we know that at least 90% of the universe is something we don't know what it is.
In the late 1970s, astronomer Vera Rubin and her associates noticed something peculiar on the outer edges of spiral galaxies like our own. Like flotsam caught in a whirlpool, stars on the fringes of galaxies should be moving more slowly than stars at the center. But what Rubin saw appeared to defy the laws of physics. The stars on the edge were moving just as fast as those in the middle.
We live, sort of 2/3 of the way, we being the Earth, about 2/3 of the way out from the center of our galaxy, and we're orbiting at 500,000 miles an hour. That's pretty fast.
Faster than it should be. Such velocities could only be caused by an enormous gravitational pull, which requires more matter than anyone had detected out there. A lot more.
It was a shock to learn that when we were studying the universe, we really weren't studying the universe. We were studying just the 5 or 10% of it that was luminous. So it's like, I don't know, trying to study the Earth and just looking at Pennsylvania.
All the things we have ever observed in the universe, the planets, the stars, the galaxies, the clusters of galaxies, make up 10% of the universe, maybe less. Early efforts to track down the missing matter failed. They call the 90% that is not visible dark matter. But no one knew what it was. Maybe dead dark stars, or some kind of cosmic dirt, or maybe a whole lot of something extremely small is filling space. Subatomic particles called neutrinos might make up part of the missing mass, but not enough. Scientists went looking for other candidates. Daniel Snowden-Ift theorizes that dark matter may be made of something physicists have taken to calling WIMPs, short for weakly interacting massive particles. These would be things smaller than atoms, if they exist at all. The only way to detect them would be to look for their footprints.
It's kind of like a ghost particle. It passes through matter without ever interacting with it, or I should say hardly ever interacting with it. Every once in a while, a WIMP will come in and bump an atom out of wherever it's sitting, and that's the only indication that we would have that WIMPs exist.
I would like to think that in 10 years we know what the dark matter is, but I wouldn't bet very much money on it. But advances usually come in very surprising ways.
Why do we care about something that we can barely measure and can't see at all? Because it might tell us how the universe is going to end. Matter makes gravity, and gravity is the only thing that can act as a brake on the expansion started by the Big Bang. If there is not enough dark matter, the universe may go on expanding and cooling to end not in a bang, but a shiver. If there is enough dark matter, the expansion of the universe will coast to a stop and reverse, everything falling back together, till the Big Bang ends in a big crunch, and maybe just possibly a new Big Bang to start things up again. Albert Einstein, among other things, revolutionized the way we think about good old gravity.
Astronomers generally only talk about one force, and that's gravity. And the reason for it is almost everything that's important on the large scale, that is on the scale of planets and stars or the universe as a whole, is gravity.
From Einstein, we know that the gravity that pulled Newton's apple down from the tree isn't a kind of magnetism. Gravity is a property of matter and space. Matter bends space. The more mass, the more space around the mass is warped. That's why the moon goes around the Earth. It's trapped in a dimple in space, a gravity pit created by the mass of the Earth. When enough matter collects, gravity is strong enough to squish hydrogen atoms into helium atoms. This fusion releases enough energy to turn on a star. But gravity is also a star killer.
Stars are born, age, evolve, and eventually die, just like people. They have a regular life cycle. During the entire life of any star, there is this delicate balancing act, because gravity is always at work trying to crunch the star down into a small point, and the high internal pressures are trying to blow the star up and blow it apart. And for about 90% of the life of the star is in nearly perfect equilibrium. And it just sits there, burning away and producing radiation.
But when the fuel is gone and the fires go out, gravity is free to collapse the star. A medium-sized star like our Sun will burn steadily for 10 billion years. Then, in a kind of cosmic spasm, it will puff up to engulf the inner planets before collapsing into one of those white dwarf stars. A star twice the mass of our Sun would collapse even farther, ending up as a super-dense star the size of New York City, a neutron star. A teaspoonful of stuff from a neutron star would weigh 100 million tons. But what happens to a bigger star when its fires die down? Say a star 50 times the size of the Sun. It may blow up as a supernova, leaving a neutron star, but then it keeps on shrinking to infinity. An infinitely small point with a gravity so powerful that not even light can escape. There's no there. It's a black hole.
And the analogy that we have to space being stretched by the material is you have a rubber sheet and you put a ball on it and it causes a dent. Put a heavier ball, it'll cause a deeper dent. If you put a heavy enough ball, it'll just tear through the rubber sheet altogether. If you force too much matter into a limited amount of space, it'll just tear space like tearing the rubber sheet.
You can be forgiven for thinking a black hole is some sort of weird science trick. An infinitely small, invisible star defies common sense. It's what happens when you use mathematics as your lens on the universe. But out here on the high desert of New Mexico, they've found that black holes do exist outside of equations. 27 giant radio dish antennas, each 80 feet wide, are positioned over 13 miles to form a single huge radio telescope. They call this very large array of antennas the VLA, which stands for the Very Large Array of Antennas. James Moran is one of the world's foremost radio astronomers.
The VLA has had a tremendous impact over the last 15 years. It's very important because it has tremendous versatility. This technique of radio interferometers was developed after World War II, but this is the first really big array. Dust obscures light rays, but this instrument can penetrate that dust because radio waves go right through the dust, and we can see down to the core of things that can't be seen in optical astronomy, for example.
It turns out that a black hole can create radio signals as it sucks in matter. The signals can show up as a beam of microwaves, a microwave laser, or maser.
Why you would find a maser in a black hole is a complete mystery. I don't think anybody would ever have predicted this. What we have found is that there's actually a very light molecular cloud in a disc shape. My friends refer to it as the maser frisbee. We didn't go looking there hoping to find something coming out of a very compact region around the black hole. It just plopped onto our computer printouts.
A black hole can attract dust and gas in its neighborhood into a whirling disk of molecules. Those molecules release great bursts of radio energy as they are drawn in. There seem to be black holes made not from single stars, but from whole clusters of stars. They have a mass 100 million times that of our sun. But these monsters are still infinitely small points, capable of gobbling up other stars. But where does the stuff that falls into a black hole go? Does it just fall out of the universe? Possibly. Or it may pop up somewhere else in space. If you'll excuse an indelicate metaphor, there may be white holes regurgitating matter eaten by black holes in another part of the universe, a wormhole in the fabric of space and time, allowing you to go from one location to another without crossing the space in between. Or it might go to another universe entirely. Astronomy's reigning theoretical genius, Stephen Hawking, proposed that the black holes in our universe might well give birth to other universes. In fact, there might be any number of universes, like bubbles in the bath. We don't know, and probably can't know. If you fell into a black hole, you'd be stretched until you were thinner than a strand of spaghetti, which wouldn't bother you because time would stop. The rules of the universe as we know them don't seem to apply to black holes. That's what happens when you start messing around with infinities. It leaves us with a universe with holes in it. A universe with a lot of room for imagination. On the sound stages of Paramount Pictures, a spin-off of one of the most durable shows in television history, Star Trek Voyager.
Very quiet on the stage. Anyone not ready?
Well, no.
Roll, please.
Rolling.
Action! I want a full systems report. And Mr. Kim, Mr. Tuvok, I want every iota of information that was recorded regarding this phenomenon. Let's see what you have, Mr. Kim.
There. It's registering only on subspace bands. We don't even have it on long-range sensors yet.
Verteron emanations. Tunneling secondary particles. It certainly looks like a wormhole.
But is it stable enough for us to enter? And if it is, where does it lead?
There is, of course, a 75% chance a wormhole will not lead to the Alpha Quadrant.
Great. Changing Jennifer's mark.
That'll be Jennifer's mark.
Yes, I gave that to her. I changed
Thank you.
it.
Great.
Real-world astronomers have confirmed now there are planets circling other suns. The problem is, we can't get to these other worlds in any reasonable amount of time. 20th century physics says nothing can go faster than the speed of light.
You want black wrap that? Sure, go ahead.
But that would be much too slow for a 24th century operation like Star Trek.
The dramatic need of a television series called Star Trek is that we need to travel to a different planet every week. So Gene Roddenberry said, well, okay, we're going to have something that he called warp drive, which somehow warped space and let us travel through subspace. How does this work? We don't know. But nevertheless, we see it work every week, and hopefully the audience buys it.
A lot of scientists love this show and have even written books showing how Star Trek physics might work.
Take anyone? Felix, what happened to you?
After all, it wouldn't be science fiction if it didn't have science in it.
Any analysis yet, Ensign?
Too far away. We'd have to be within 1,000 kilometers to get a detailed analysis. But that would mean a significant course change.
Well, Mr. Kim, if there's even the possibility of finding a wormhole, I think we can afford a detour.
Scientists take wormholes seriously enough that they have become an assignment in George Smoot's physics class. Given a wormhole a couple of miles across, students are asked to calculate what could pass through without being destroyed by gravitational tides.
the smallest piece of electronic that wouldn't be torn apart in terms of going through this? And the answer was, it's something that's smaller than a chip, but it's roughly the size of a chip. And so, you know, in science fiction shows, they just show small wormholes that you go into, but in reality, the wormhole would have to be quite huge.
But theoretically, at least, you could go someplace else in space or time. As far as physics goes, a wormhole is a loophole in the laws of the universe. So we are left with questions. Why do some stars appear to be older than the universe? Why do galaxies move as if there were something dark and huge out there?
We're not making people live 200 years. We're not doubling the gross national product. What we are doing is enriching everybody's lives by trying to answer some of the questions that I think everybody's interested in.
These are some of the oldest questions, children's questions. Where did we come from? Where are we going? Are there other worlds? What is outside the universe? What happened before the universe started? What happens after the universe ends?
You want to find out, well, where does science end and where does philosophy take over? And it's not clear where they do.
Modern astronomy is a young subject, and each time we get a new and better tool for looking into the void, we find surprises. More and more data that doesn't quite fit.
And I think it's portrayed as if the field is in total confusion and chaos, and I think very often it appears that way at the forefront when things are not understood and there are unsolved problems. But progress is being made.
The fact that we're able to take these subtle clues, that things you can barely measure with the biggest, most sophisticated instruments, and figure out that they are telling you about what the universe was like 15 billion years ago, I think that's a terrific thing.
Why does the universe exist? Given the fact that it does exist, the fact that it is as exquisitely beautiful, as exquisitely tuned as it is, that it works as astonishingly well as it does, and that we, very tiny creatures on a rather remote planet, not in any special place in the universe, have been able to evolve in this universe and sense the universe, the entire universe around us, that we can sense that there are things out to 15 billion light years away from us. That to me is just a mind-boggling concept.
We are part of the universe. The material that we know, the matter we're made of, started out as atoms produced by exploding stars.
I like very much the fact that every atom in our bodies has come from some star. If there were no stars, the universe would be all hydrogen and none of what we know would exist.
And that's why it's not an exaggeration to say that human beings are stardust, because the iron in our blood and our hemoglobin and the calcium in our bones and all the other heavy elements in our body were created in supernova explosions.
So in our quest to understand the universe, we come back to ourselves. If we are made from the elements of stars, aren't we then, in a way, the universe trying to understand itself? It's not quite what the ancients were talking about, but maybe we're in the center of the universe after all.